Welcome to everybody. This is Dr. V. Ayyambillai, Professor EC, GRIT Hyderabad. The course name is Probability and Stochastic Processes. First we will see probability. In this session we will see introduction to probability, different approaches of assigning probability. Let's go for an introduction to probability. Randomness and uncertainty exist in our lives and in every discipline of science, engineering, and technology. Probability theory is a mathematical framework that allows us to describe and analyze random phenomena in the world around us and to design and analyze systems. Probability concept is associated with four things: experiment, outcomes, sample space, and event. An experiment involves procedure and observation. A random experiment is an action or process that leads to one of many possible outcomes. Examples: flipping a coin. In this experiment, outcomes are heads and tails. Rolling a die. In this experiment, outcomes are numbers 1, 2, 6. Exam marks. In this experiment, outcomes could be from 0 to 100, both inclusive. Course grades. In this experiment, the outcomes could be F, D, C, B, and A. Task completion times. In this experiment, outcomes could be any non-negative values of times. Next, let's see what are sample space, outcomes, and events. The set of all possible outcomes of an experiment is called the sample space. We will denote the outcomes by O1, O2, and so on, and the sample space by capital S. Thus, in set theory notation, S is equal to O1, O2, and so on. An individual outcome in the sample space is called a simple event. An event is a collection or set of one or more simple events in a sample space. We may not be interested in simple events, rather in a collection of simple events that has some characteristic. Example: roll of a die. In this, the simple events or outcomes are 1, 2, and so on up to 6. The events that may be defined by us could be like: outcome is an odd number, outcome is an even number. And we can also define in some other ways. Next, let's see assignment of probability. First, axioms. There are three axioms to be seen. Given a sample space capital S is equal to O1, O2, and so on, the probabilities assigned to events must satisfy the following requirements. 1. The probability of any event must be non-negative. That is, P of y greater than or equal to 0 for each I. 2. The probability of the entire sample space must be 1. That is, P of S is equal to 1. Let there be n events. Let the events be defined as A1, A2, and so on up to A capital N. Let all these events be mutually exclusive or disjoint. In that case, a small m intersection a small n is equal to a null set for all m not equal to n. Then P of A1 union A2 union and so on union A capital N is equal to P of n is equal to 1 to capital N union A small n is equal to sum of individual probabilities, that is sigma small n is equal to 1 to capital N P of capital A small n. Now, what are the approaches of assigning probability? There are three ways of assigning probability. 1. Classical approach or set theory. 2. Relative frequency approach. 3. Subjective approach. Let's see the classical approach first. If an experiment has small n simple outcomes, this method would assign a probability of 1 by small n to each outcome. In other words, each outcome is assumed to have an equal probability of occurrence. This method is also called the axiomatic approach. Example 1. Roll of a die S is equal to 1, 2 and so on up to 6. Each simple event has a 1 by 6 chance of occurring based on the principle of equal likelihood. Next, let's see an example of two rolls of a die. In this case, S is equal to 1, 1, 1, 2 and so on up to 1, 6, then 2, 1, 2, 2 and so on, so up to 6, 6. In this, each simple event has a probability of 1 by 36. Next, let's see a relative frequency approach of assigning probability. In this case, probabilities are assigned on the basis of experimentation or historical data. Formally, let A be an event of interest and assume that you have performed the same experiment small n times, so that small n is the number of times A could have occurred to a maximum extent. Further, let small n capital A be the number of times that A actually did occur. Now, consider the relative frequency small n capital A divided by small n. Then, in this method, we attempt to define P of A as P of capital A is equal to limit small n tends to infinity small n capital A divided by small n. The above can only be viewed as an attempt because it is physically not feasible to repeat an experiment an infinite number of times, as the equation limit n tends to infinity na by capital Na by n says. Another important issue with this definition is that two sets of n experiments will typically result in two different ratios. However, we expect the discrepancy to converge to 0 for large values of n. Hence, for large n, the ratio small n capital A divided by small n may be taken as a reasonable approximation for P of A. Let's see some examples. Roll of a die. In this, capital S is equal to 1, 2 and so on up to 6. Roll the given die 100 times and suppose the number of times the outcome 1 is observed is 15. Then capital A is equal to 1, n capital A is equal to 15 and small n is equal to 100. Therefore, we say that P of A is approximately equal to 15 by 100 is equal to 0.15. Next, let's see an example of computer sales. A computer store tracks the daily sales of desktop computers in the past 30 days. The resulting data is as follows. Desktop sold 0, number of days 1. Desktop sold 1, number of days 2. Then 2 desktops sold in 10 number of days. 3 desktops sold on 12 number of days. 4 desktops sold on 5 number of days. 5 or more number of desktops sold on a single day. Number of days is equal to 0. Now the approximate probabilities. Please note, we are telling approximate probabilities. The approximate probabilities are 0 desktop sold 1 by 30, then 1 desktop sold 2 by 30, 2 desktops sold 10 by 30, 3 desktops sold 12 by 30, 4 desktops sold 5 by 30, 5 or more desktops sold 0. Thus, for example, there is a 40% chance that the store will sell 3 desktops on any given day. Finally, let us see the subjective approach of assigning probability. In the subjective approach, we define probability as the degree of belief that we hold in the occurrence of an event. Thus, a judgment is used as the basis for assigning probabilities. Notice that the classical approach of assigning equal probabilities is in fact a particular scheme of assigning probability based on a judgment, where the judgment is equal likelihood. What is somewhat different here is that use of the subjective approach is usually limited to experiments that are not repeatable. Let's see an example of a bicycle race. Consider a bicycle race with 8 persons participating. What is the probability for a particular cyclist to win? Is it reasonable to assume that the probability is 1 by 8? Note that we can't apply the relative frequency approach because we can't repeat the experiment. It takes a lot of time in repeating. People regularly place bets on the outcomes of such one-time experiments based on their judgment as to how likely it is for a particular cyclist to win. Indeed, having different judgments is what makes betting possible. In a box, there are 80 resistors, each having the same size and shape. Of the 80 resistors, 18 are 10 ohms, 12 are 22 ohms, 33 are 27 ohms and 17 are 47 ohms. If the experiment is to randomly draw out one resistor from the box with each one having equal likelihood to be drawn,